طيب, the first chapter deals with lattice energy. Now, what is lattice energy? Lattice energy, we say it is the energy released. It is the energy released when 1 mole of an ionic compound, when 1 mole of an ionic compound is formed from its ions, is formed from its ions in the gaseous state, in the gaseous state. Yani lattice energy is the energy released, because always lattice energy will be an exothermic reaction. It releases heat energy. So the lattice energy is the energy released when 1 mole of an ionic compound is formed from its ions in the gaseous state. So if we'd like to write, for example, the lattice energy for example, sodium chloride, of course, here we have to say 1 mole of a solid. We have to say here of a solid ionic compound. So here sodium chloride solid is formed from its ions, which are the sodium ions in the gas state, plus the chloride ion in the gas state. We call this enthalpy change. We call it the enthalpy change of lattice energy, or just we call it lattice energy. And it's better to call it enthalpy change of lattice energy, but if we say lattice energy only, it's okay. So we say it is the energy released. Why is it energy released? As I told you, because it's an exothermic reaction. And why is it exothermic? We know that whenever any bonds are broken, then it requires energy, and this is an endothermic process. But if a bond is formed, then energy is released. Hello, Yajudi. I allowed you recording, Yajudi, if you'd like to. Okay, so we just started. Yes, Yajudi. We started our first chapter here is the lattice energy and how to calculate this lattice energy. Now, what is meant by the lattice energy? We say that the lattice energy is the energy released when 1 mole of a solid ionic compound is formed from its ions in the gaseous state. We see that whenever an ionic compound in the solid state, 1 mole of an ionic compound in the solid state is formed from its ions, then as I told you that if a bond is broken, it requires heat energy and it's an endothermic process. But when a bond is formed, it will be an exothermic process. It will release heat energy. So the energy released when 1 mole of an ionic compound, solid ionic compound, is formed from its ions in the gaseous state, we call this the lattice energy. Another example, for example, if 1 mole of magnesium chloride, for example, is formed from its elements, also is formed from its ions, also in the gaseous state. So here we have magnesium ion plus 2 chloride ion in the gaseous state. It releases heat energy, and we call this the lattice energy. We will see that in case of sodium chloride, we'll see that the lattice energy, in case of the sodium chloride formation is equal to minus 787. Of course, we do not have to memorize these values, ولكن I just give it to you to show you the difference between the amount of energy released when sodium chloride is formed and when something like magnesium chloride is formed. We'll see that the amount of energy released is equal to minus 2,526 kilojoules per mole. So it depends on the ionic compound that is formed, the amount of energy is released. Now, if we look at both sodium chloride and magnesium chloride, for example, we see that the amount of energy released in case of the magnesium chloride is much greater than that. It's about maybe more than 3 times the amount of energy released when sodium chloride is formed. So can you give us any opinion of you? Why does the magnesium chloride lattice energy is much exothermic than that of the formation of sodium chloride? Do you have any opinion? Or any يعني idea? Why? يعني what do you see the difference between sodium chloride and magnesium chloride? Yes, يا أسيل.
In sodium chloride, there's only one positive and one negative ion.
Yes.
But in magnesium chloride, there's two of each.
Yes, excellent. You mean the positive charge and the negative charge, isn't it?
Yeah, two positive ions, sorry, and two negative ions.
Yes, excellent. So as Asil said, if we look at sodium chloride, we will see that it has only one positive charge on the sodium compared to two positive charges on the magnesium. So this means that the more the positive charge, the more the positive charge on the metal ion, then the higher will be the energy released. And here, the second factor, so factors affecting the lattice energy, or the value of the lattice energy. The first thing is the charge of the ion, the charge of the ions. Yani the more the charge, as we see here in magnesium, the more will be the energy released. So the more the charge, the greater will be the energy released. Greater lattice energy. It will be the greater the energy released. If we say this lattice energy like this, يعني عشان بعد كده always we write lattice, يعني for me to write lattice energy instead writing lattice energy completely. So the charge on the ions, the more the charge, the greater will be the lattice energy. Now, what else? Asil said that here the sodium, or every sodium has only one chloride to be attracted to, but for magnesium, we have two chloride ions. So the ratio between the cations and the anions also differs. Between the cation to the anion, of course, the greater the ratio, also the greater will be the lattice energy. And what else? There is a third factor affecting. What else? And if you can deduce, what else? Okay, it's the size or the radius of the ion. The radius of the ion, of the ions. The smaller the radius, the radius, the greater will be the lattice energy. The greater the lattice energy. Okay, so as you see here, there are three factors affecting the value of the lattice energy that is released when positive and negative ions react together to form 1 mole of an ionic compound, 1 mole of a solid ionic compound. It is the charge on the ions. The more the charge on the ion, the greater will be the energy released, the lattice energy released. And the ratio between the cation and the anion, here you see that the ratio is 1:1, but here the ratio is 1:2. So also the more the ratio between the ions, the greater will be the lattice energy. And the radius of the ions differs so much. The smaller the radius of both the positive ions and the negative ions, the smaller the radius, the greater will be the lattice energy. So you see that magnesium ion has a smaller radius than the positive sodium ion, as we know from AS. As more electrons are released, so the nuclear charge on magnesium will be greater than the nuclear charge on sodium, because here we will have 12 protons. Yani if we write here that we have 12 protons and 10 electrons compared to 11 protons and 10 electrons. So of course, whenever we have more nuclear charge, the ionic radius will be smaller. So the ionic radius of magnesium ion is smaller than the ionic radius of the sodium ion. The chloride, of course, is common, but since the magnesium ion radius is smaller, because the attraction force here, of course, between the protons and electrons is greater, so the greater also will be the lattice energy. Of course, the more the value of the lattice energy, of course, more it is negative, the more it is negative. This means that the attraction force between the positive ions and the negative ions are very big. Okay, so this value indicates that the attraction between magnesium and chloride ions is much greater than the attraction force between sodium ion and chloride ion. Now, if we want to determine the lattice energy of any ionic compound, we have to know some definitions, like exactly when we studied about the Hess's cycle. We had to know some of the information about enthalpy change of combustion, about enthalpy change of hydration, or enthalpy change of not hydration, but formation, combustion, bond energies. As we studied these things in AS, also in order to calculate the amount of lattice energy that is produced by the reaction of the positive and negative ions to form the solid ionic compounds, we have to know some of the definitions. We have to know some definitions. What are these definitions that we have to know? The first definition is to revise the ionization energy. We want to revise the ionization energy. Does anyone remember what is the ionization energy? I'm going to write it IE. Does anyone remembers what's ionization energy? Okay, someone else other than Asil? Ahmed, do you know what's the ionization energy? Do you remember it? Yes, Fadda.
Yeah. Is it needed to remove an electron from an atom?
Yes, excellent. It is the energy required to remove 1 mole of electrons from every atom, or from each atom in 1 mole of atoms, to form gaseous positive ions, isn't it? So they are not going to ask you to write the definition of the ionization energy, but it says that it is the energy required. It is the energy required to remove 1 mole of electrons, 1 mole of electrons from every atom in 1 mole of gaseous atoms to form positive ions, to form positive ions. It means that here also the atoms must be in the gas state. And for example, if I want to form the sodium from the sodium atom in the gas state, then using the first ionization energy, then it will remove an electron from the sodium atom and forms sodium ion in the gas state plus electron. This is called the first ionization energy, to remove the first electron. But if I have something like magnesium, for example, then magnesium, by the first ionization energy, is going to remove an electron, forming magnesium ion in the gas state plus electron. And then we know that magnesium would like to have a +2 charge, so magnesium ion in the gas state, by the second ionization energy, it forms the magnesium +2 ion in the gas state plus another electron to be removed. And of course, if we have something like aluminium, it will require 3 steps in order to remove 3 electrons and form the aluminium +3. But what is very important is that these atoms must be first in the gas state before we remove the electrons out of them. So this is the first method. This is the first definition that we have to know in order to calculate the lattice energy, because the lattice energy cannot be determined directly. We cannot determine the lattice energy of any ionic compound directly. We have to do something like a cycle, like Hess's cycle, but this year we are going to study another cycle. It's similar, very similar to Hess's cycle, but we are going to call it the Born-Haber cycle, of course, because the scientists who did it were called Born and Haber, so that's why they called it the Born-Haber cycle. It's similar to the Hess's cycle, because as we cannot determine the lattice energy directly, so we have to find another route And from this other root, we can determine the lattice energy, as we are going to see. So the first definition that we have to know is the ionization energy. Now, what is the second definition that we have to know? It is something called the enthalpy change of atomization. The enthalpy change of atomization. Now, what is the enthalpy change of atomization? We say it is the enthalpy change. It is the enthalpy change when, as you see, atomization means atom. When 1 mole of atoms in the gaseous state, is formed from its element, in the standard physical state, in its standard physical state. So what does this mean? It is the enthalpy change when 1 mole of atoms in the gaseous state is formed from its element. So for example, if I want to form a sodium atom in the gas state, so what is the element of sodium, ya Sujud? What is the element of sodium? It is sodium. But is it sodium present, the sodium metal, is it present in the gas state or what? Yes, Sujud, is the sodium metal present as a gas state or liquid state or a solid state?
Solid.
Yes, of course, it's solid. Excellent. So it is a solid. So if you change a sodium solid to sodium gas, this requires energy that we call it the enthalpy change of atomization. Enthalpy change of atomization is the change of element, whatever by it is present in which form. Is it present in the solid state or a liquid state or even in the gas state, to produce 1 mole of atoms in the gas state? It must be 1 mole of an atom in the gas state. If I want to change, for example, magnesium, I want to change it to 1 mole of magnesium atom in the gas state, then this is formed, this magnesium atom in the gas state is formed from the magnesium, which is a solid at the beginning, by what we call the enthalpy change of atomization of magnesium. But what if I have, for example, something like chlorine? What is the standard physical state of chlorine, ya Asil?
Gas.
Yes, it's a gas, but is it Cl gas or what?
It's Cl2.
It's Cl2. Excellent. Chlorine as an element is Cl2. It is Cl2 gas. And so we want to change it to 1 mole of an atom of chlorine in the gas state. But of course, here we have Cl2. So this means that it must produce 2 chlorine atoms. But our definition says that it is the enthalpy change when 1 mole of atoms are produced from its element. This means that I cannot write here 2. So this means that I have take here half of the chlorine gas to produce 1 atom in the gaseous state, and we call this the enthalpy change of atomization of chlorine. Okay. For example, bromine. If I want bromine, 1 mole of bromine atoms in the gaseous state, it is formed from its element. So what is its element, ya Ahmed? Bromine.
So it's half Br2.
Excellent.
Yeah.
It's half Br2. And what is the physical
Liquid.
state? It's a liquid.
Liquid.
Excellent. It's a liquid. Bromine is a liquid. And so we take half bromine. So if you are dealing with metals, then the enthalpy change of atomization means just converting the metal solid to the metal gas. But if we have something non-metal, then we have to change its we have to take half of its formula in order to get it in the 1 mole of gaseous atoms, and this is done by the enthalpy change of atomization. Okay, so this definition also we have to know. It's very useful in the cycle that we are going to do. Now, another definition also that is important is, Awal, do you have any question of what I said up till now? You have any question?
No, it's understood.
Okay,
No.
thank you so much. Now we have something called the electron affinity. Also, we have to know about electron affinities. We know that the ionization energies is for metals. Yani it's always the metal that loses electrons to form positive ions. So we call this ionization energy, the energy required to remove an electron. Now, the electron affinity is the opposite of that. The electron affinity is when a non-metal accepts an electron or gains an electron or more, of course, to form negative ions. It's when a non-metal accepts an electron, or we can say that we have, for example, the definition of the first. We have also first electron affinity and second electron affinity, just like first ionization energy and second ionization energy. We say that the first electron affinity, we are going to give it the symbol EA1, first electron affinity. It is the enthalpy change. It is the enthalpy change when 1 mole of electrons, I write electrons in this way, is added to 1 mole, of gaseous atoms, to form 1 mole of gaseous, negative ions, Okay, so here, for example, when I have a chlorine atom in the gas state, it will gain an electron to form chloride ion in the gas state also. And here we see that the first electron affinity for this gaining of electrons will be minus 348 kilojoules per mole. And if I have, for example, sulfur in the gas state, it gains an electron to form, by the first electron affinity, it will form sulfur ion in the gas state. And this first electron affinity is equal to minus 200 kilojoules per mole. So here we are dealing with the first electron affinity. You will see that always the first electron affinity is a negative value. It means that when the atom gains the first electron, we are dealing here with the first electron affinity only. In the first electron affinity, we will see that the first electron affinity is always negative in sign. It means that it's an exothermic reaction. It's an exothermic reaction because it is something that the atom, the gaseous atom, would like to do. The chlorine atom has 1 electron less than the nearest inert gas. So when it gains this electron, this is something very happy for it. And so it releases heat energy due to this formation where the electron goes to the chlorine atom to form the chloride ion. This is something very good for the atom because it becomes more stable than before. That's why it releases heat energy. The same for any atom. If I take, for example, oxygen plus electron gives the oxide negative ion in the gas state. We see that this electron affinity is equal to, this is EA1. This is the first, we are talking about the first electron affinity. This is also equal to minus 141 kilojoules per mole. But if the oxide negative ion gains another electron to form the oxide ion that which the oxygen would like to form, then we will see that the second electron affinity is going to be a positive value, plus 798 kilojoules per mole. So as you see here, the first electron affinity is always a negative value. The first electron affinity is always a negative value, but you see that the second is always positive. The first electron affinity is always a negative value. Always when an atom gains the first electron, it will release an amount of energy depending on the atom. Of course, we are going to discuss when it will produce more energy than the other, because this is something that the atom would like to do. It would like to have an electron to be more stable. It would like to gain an electron to be in a step to make it more stable, like in case of sulfur or in case of oxygen. It gained an electron in a step to be more stable. So we will see that it releases heat energy. But why does it become a positive value when it gains the second electron? Although this is much more required, the oxygen would like to gain 2 electrons, not only 1, in order to be in the form of oxide ion, which has the full outer shell electrons. So why does it become a positive? Why it is required that we must force the oxygen negative ion to gain this electron? Who can tell me? Why here the second electron affinity is a positive value? What do you think? You don't know, isn't it? Okay. If you look at the oxygen negative and the electron, both of them carries what? Both of them carries negative charge.
They're both negative, so they repel?
Yes, excellent. I see it as oxygen negative and the electron negative are both negative, so they will repel each other. When the electron is approaching the oxygen negative, although the oxygen negative wants this electron to become an oxide ion, yet due to its negative charge, it will repel the negative charge on the electron, and that's why we will find that the second electron affinity is always positive. It must be forced. The oxygen negative must be forced to gain this electron to become oxide negative 2. So it requires heat energy in order that this electron go inside the oxygen negative ion to become the oxide ion. So always, you will see that the first electron affinity is a negative value, but the second electron affinity is always a positive value. Why different atoms have different values of the first electron affinity? Why some of them releases more heat energy than the other when it accepts or gains an electron? For example, if we take examples, for example, if I take the electron affinity, the first electron affinity of some of the ions, for example, if we have an oxide ion, or oxygen, then its first electron affinity to gain an electron is minus 141.1. For sulfur, it is minus 200.4. For selenium, it is minus 195. For tellurium, it is minus 190. If we look, for example, for the first electron affinity of the halogens, we will find that fluorine is equal to minus 328. Chlorine is minus 348.8. For bromine, it is minus 324.6. And for iodine, it is minus 295.4. Minus 295.4. So you will see what? You will see that starting from the chlorine, for example, you will see that the value of the electron affinity, the release of the amount of energy due to the attraction of an electron towards the atom, it becomes less. As we go from chlorine, it means that the chlorine compared to the bromine, compared to the iodine, the chlorine is the one that would like very much to gain the electron. That's why it releases more electron affinity, more than when the bromine gains this electron. And this is more than when the iodine gains the electron. Now, why? Why the chlorine is having the highest electron affinity? Why does it produces more heat energy when an electron is accepted inside its atom? That's because if you look at the chlorine is present in period 3. Yes. يعني يا سجود, you are not one of the group. You just يعني joined us just like that, يعني to يعني just to hear, يعني I thought that you are one of the group.
No, I didn't know which year it was.
يعني you came from يعني you came from another يعني from a center or something like that, يعني from where did you يعني know that we are having a lesson?
I'm doing AS level now.
You joined what?
I'm doing AS level now. I thought this was AS level.
ايوه, يعني انت جايه تبع سنتر حط اعلان فانت جيتي تبعه ولا ايه؟ مش واخده بالي.
لا. أنا بس مامتي شفت في الجروب افتكرت الحصة بتاعت AS level مش A level.
اس كامبريدج يعني. اوكي تمام. اوكي خلاص,
مع
اتفضلي يا
السلامة.
سجود, مع السلامه, باي باي. اوكي, امال اسيل, انت قلت ماما قالت لي ان انتوا 3 في الجروب مش 2 بس.
أيوة احنا 3 بس ما في
السلام عليكم.
عليكم السلام, اهلا وسهلا, ازي حضرتك؟
كيفك؟ الله
الحمد
يسلمك يا
لله,
رب.
اهلا وسهلا بحضرتك.
الحمد لله. احتمال محمد يكون يعني افتكروا انه توقيت ساعتين من مصر مش ساعة، فانا اتصلت على امه قلت لها خليه يدخل،
عشان
هو
احنا
يمكن
النهارده
لخبط في الزمن.
يعني عشان موضوع النهارده يعني موضوع اساسي, يعني عشان كده انا حتى لما حضرتك قلتي
ما
ان
هو عشان
احمد لسه
كده
عنده
واحنا
امتحانات,
ايوه
انا ما
اخرنا.
رضيتش ابدا.
بالظبط،
مم.
ما عشان كده احنا تأخرنا بسبب انه محمد كان عنده امتحانات، وانا لما تأخر في الدخول اتصلت على امه قبل شوية، قلت لها قلت يمكن لخبطوا في انه ساعة وساعتين. وربا برضو كان مفروض تدخل، رسلت لأمها برضو، فما عارفة اللي حصل شنو. بس يمكن محمد يدخل، حتصل عليها تاني.
امال احمد انت مش تبعهم يا احمد؟
أحمد معانا. أحمد والدته أمل، ومحمد والدته شيرين،
اه,
وفي سحر وبنتها ربا مفروض تدخل برضو. فأنا هشوف أم محمد
عشان انا
وأكلمها
مش
تاني إنه
حاضر,
يدخل.
يعني انا مش حاضر اعيد حصه تاني الحقيقه, يعني
طيب
يعني لان
حاضر، أنا
الماده
هشوف.
الماده بتبقى يدوب على ان انا ايه اقول كل
أكيد.
مره. فيعني معلش, عشان يعني يحضروا, عشان الحاجه دي مهمه وهيعتمد عليها كمان الحصه الجايه, ويمكن كمان نص الحصه اللي بعدها, فيعني
حاضر، أنا هتصل
اوكي.
عليها تاني.
اوكي, شكرا
أوكي
جزيلا
تمام.
لحضرتك, متشكره خالص. طيب, now we said why is the first electron affinity is greater than the first electron affinity in case of the bromide and more electron affinity than in case of iodide. If we look at the chloride, we see that the chloride is present in the third period. The chloride is present in the third period. Okay, and the bromide is present. If we look at the bromide, we'll see that the bromide is present in the fourth period. It means that there are more shells when it is present in the fourth period. This means that there are more shells in the chloride, in the bromide, compared to the chloride. And this is the bromide, and this is the bromine atom, and this is the chlorine atom. Now, both of them would like to accept an electron in order to change to the bromide ion or to the chloride ion. So which one of them would you expect? Which one of them would you expect to accept the electron more easily? Will it be the chloride or the bromide? Which one, ya Asil?
Bromide.
The bromide would accept the electron more. Okay, what do you think, ya Ahmad?
Chloride.
The chloride. Why, ya Ahmad, did you thought that the chlorine atom would accept the electron more readily or more easily?
Because it has a less atomic radius, فالtendency to attract an electron.
Yes, excellent. Because the distance here between the nucleus and the outer shell at which the electron is going to enter, because you know that whether it is chlorine or bromine, it has 7 electrons in the outermost shell. isn't it? And so this electron wants to come here and join the other 7 electrons of the chlorine atom. And since the distance between the outer shell at which the electron is going to enter and the nucleus is smaller, so the attraction force of the positive nuclear charge and this electron will be the greatest, will be greater than that in case of bromine, because here the distance between the electron that is entering and the positive nucleus, the distance is bigger. And so the attraction force between the positive nucleus and the electron is smaller than the attraction force between the positive nucleus and the outer electron. Okay, here the attraction force is smaller. We know that the more the attraction force, the more will be the energy released by the atom. That's why the chlorine atom has a higher electron affinity more than the bromine atom. Because when the chlorine accepts an electron and transfers to the chloride ion, acceptance of electron is something that is wanted, because the distance between both of them would like to have an electron. But the distance here between the nucleus or the nuclear charge and the entering electron, the distance is small. And so the attraction force here will be greater than the attraction force here. And when the attraction force is greater, the greater will be the electron affinity. If this is the case, why in case of fluorine, we find that the electron affinity is smaller than that in case of chlorine? In case of fluorine, we have only, so this is the nucleus, we have only 2 shells, not 3. So the distance should be smaller. And this means that the incoming electron, there is here also 7 electrons that are present here. And there is an electron that wants to enter the atom and form the negative ion. And of course, the fluorine would like to have this electron, but we will see that the energy released when the fluorine atom gains the electron is less than the electron affinity when the chlorine atom gains this electron. So why is this the case? This is the case because the fluorine atom is a small atom. Its radius is small. And so the small radius, it has already 7 electrons filling it. So they do not need an 8th electron to be with them in the same small radius. This radius is so small. Maybe I've drawn it, of course, in a big way to explain, but the radius of the fluorine atom is so small. So if an electron would like to join the 7 electrons that are already present in the atom, this means that this electron will not have a place to go in. The place here is so small. So the incoming electron does not have a space to go in, although the fluorine atom would like very much to attract this electron to become a fluoride ion. So it will do so. The fluorine will gain the electron and become fluoride ion. But because there is no space for this electron to enter, because the size of this shell is so small, and also the electrons present are moving in this small size, they do not want any more electrons to come and be with them in the same small size. That's why they try to repel it, although the fluorine atom as a whole would like to gain this electron. So at the end, it will gain the electron and release energy, but the energy released is less than the energy released by the chloride ion, or the chlorine atom. So we have to know about the chlorine atom and the bromine atom is that, as I told you here, that as the distance here in the chlorine atom between the nucleus and the incoming electron is smaller than the distance between the incoming electron and the nuclear charge here or the nucleus here, then the electron will be attracted by the chlorine atom more than the attraction between the electron and the nucleus in the bromine atom. That's why the chlorine atom will release more energy than the bromine. Okay, understand, or shall I explain it once more? Type. When I said here for oxygen, we said that oxygen would like to form 2 negative charges. So it forms the first charge by the first electron affinity, and it forms the second charge, it gains the second electron and forms oxide ion by the second electron affinity. And so if we are talking about that oxygen changed to oxide ion, then we have to add these two electron affinities together. So we have to add the first and the second electron affinity in order to get the amount of electron affinities that for an oxygen atom to change to an oxide ion. Okay, any question here? So these are the three definitions that we have to know in order to know how to calculate the lattice energy of any ionic compound in the solid state. So we said that to calculate calculations of lattice energy of a solid ionic compound, so we said from the definition, the lattice energy is when a solid ionic compound is formed from its ions in the gas state, is formed from its ions in the gas state. This is called the lattice energy. It is the energy released when sodium chloride solid is formed from the ions, the sodium ion positive and the chloride ion negative. Hello, Yaroba. So here, this is the amount of energy released, and we said that this is called the lattice energy. And of course, the lattice energy is so difficult to be found experimentally. Yani experimentally, we cannot make any experiment in order to determine the lattice energy directly. That's why, just as we did in AS, we studied something called Hess cycle. Also here, we are going to study the Born-Haber cycle to find another route by which we can find the lattice energy that cannot be determined directly from any experiment. So what are we going to do? What will be the second route that we are going to go through? Now we want to form sodium chloride solid. And we know that there is a different way by which we can prepare the sodium chloride, which is that we add the sodium solid to the chlorine gas. So it will form sodium chloride solid. So here, if we add the sodium metal, which is solid, to the chlorine gas, we can produce the sodium chloride in the solid state. And we say this is called the enthalpy change of formation, isn't it? You remember the enthalpy change of formation we studied in AS? Do you remember it?
Yes.
So it is the enthalpy change of formation. It is the enthalpy change when 1 mole of a substance is formed from its elements in their standard physical state. So also we have to know this, the enthalpy change of formation. So sodium chloride can be formed if we react its elements together by the enthalpy change of formation. So sodium metal reacts with half chlorine gas to form the sodium chloride solid by what we call the enthalpy change of formation. So this is a route. And there is another route, which is that the sodium chloride solid is formed from its ions in the gas state. So how can we relate these two equations together to form a cycle like that which we made in Hess's cycle and determine the value of the lattice energy and calculate? So that's what we are going to do in this part of the chapter, is to calculate the lattice energy by finding a different route by which the ionic compound is formed, and then relate these two equations together. We have to relate them together in order to find out the lattice energy. So how can we do that? Now, we said that this is a route by which, by the enthalpy change of formation, sodium chloride can be formed. And also, we can say that if we add, as we said before, that the sodium ion in the gas state plus chloride ion in the gas state, then by the lattice energy, it forms the sodium chloride. Now we want to close this cycle so that we have a cycle by which we can determine the lattice energy by knowing, of course, the enthalpy change of formation. So what are we going to do? We have to change the sodium solid to sodium gas, sodium solid to sodium gas in the form of positive ion, and we have to change the chlorine gas to chloride ion in the gas state. And in this way, the cycle will be closed. And as we usually did in AS, we say that we have a root, first root, and we have another root, which is the second root. And by equalizing both roots, we can get the enthalpy change of lattice. So by equalizing both equations, we can get the lattice energy. So how can we do that? Hello, Ya Muhammad. Is that you, Ya Muhammad, entering from iPhone? Type, okay. So as we said here, that there are two routes by which we can form the sodium chloride. The first route is that the sodium solid reacts with half chlorine gas to form the sodium chloride by what we call the enthalpy change of formation. And the other route is changing the sodium solid and the chlorine gas to sodium ions in the gas state plus chloride ion in the gas state. And then these two chloride ions and sodium ion react together to form the sodium chloride solid by the lattice energy. So how can we change this sodium solid to the sodium ion? We have taken just from a moment that in order to change the sodium solid to a sodium gas, this requires an enthalpy change that is called the enthalpy change of atomization. Yes, Yasir?
No, I was just gonna say atomization.
Yes, excellent. The atomization. We just from a moment said that in order to change the sodium solid to sodium in the gas state, then it requires an enthalpy change called the enthalpy change of atomization. So in the first step, we want to change the sodium first solid to sodium in the gas state. And as Asil said, by enthalpy change of atomization, we can change the sodium solid to sodium gas. Now, but we do not want it to be only in the form of a gas, but also we want it to be in the form of a positive ion. So what are we going to do, Ya Asil? How can you change sodium gas to sodium? Yes.
Ionization.
Yes, bravo. By the first ionization energy. So by the first ionization energy, the sodium metal in the gas state could be changed into sodium ion in the gas state by the first ionization energy. So we can do these two processes here in order to change the sodium solid to the sodium ion in the gas state. Now, what about the chlorine, Ahmed? I want to change half chlorine to chloride ion in the gas state. So what am I going to do? I have half, yes.
Atomization, right?
Excellent. By the atomization energy, enthalpy change of atomization, it will be changed to what?
First ionization energy.
No, we don't have ionization here because ionization means removal of an electron. This is the ionization energy. But by the atomization, I want to change the half chlorine to what? To the chloride ion in the gas state, isn't it?
Yeah.
How am I going to do that? By enthalpy change of atomization that changes the chlorine gas into chlorine atom in the gas state, isn't it? Yes, Ahmed?
Okay, yeah.
And then I want to change the chlorine gas to chloride ion in the gas state. So what am I going to do? What is this called? It is called electron affinity. When the atom gains an electron to form the chloride ion, this is called electron affinity, isn't it? Understand, Ahmed, or shall I explain it once more?
That's clear. Yeah, I got it.
by the first electron affinity. So in this way, we can change the half chlorine to the chloride ion in the gas state and change the sodium solid to sodium ion in the gas state. And then this cycle is now closed. We say, as we did in A level, in AS level, that the first root is equal to the second root. And by knowing all these values of different energies, we can calculate the lattice energy. Okay? Understand the idea? So let us apply it على lithium chloride, for example, or lithium fluoride. If I want to prepare lithium fluoride and calculate its lattice energy, if I want to calculate the lattice energy of lithium fluoride, what are we going to do? We are going to write بقى the Born-Haber cycle. The Born-Haber cycle to calculate the lattice energy of lithium fluoride. So in order to draw the lattice energy, to draw the Born-Haber cycle, we are going to put a line here and write lithium fluoride solid. And then, as we said here, we have two routes. The first route is through the enthalpy change of formation of the sodium chloride. So here, the lithium fluoride is formed from what? Lithium fluoride is formed from what? Acyl. From which is it formed from?
Li plus and
No,
F minus.
I want formation. What is meant by enthalpy change of formation?
Yeah, okay. Lithium solid plus half F2
Bravo.
gas.
Excellent. So as fluorine is a gas, so lithium fluoride solid is formed. It is the enthalpy change. We call it the enthalpy change of formation. It is the enthalpy change when 1 mole of a substance is formed from its elements in their standard physical states, isn't it? So this means that lithium fluoride solid is formed from lithium solid and half fluorine gas. Type. This is the first route. We said that this is the first route, the formation. Now I want to change the sodium to sodium ion gas and the chlorine to, the lithium to lithium ion gas and the fluorine to fluoride ion gas. So we are going to start, for example, with the lithium and end it up to lithium ion in the gas state and then go to the fluorine. So we start one by one. So for the lithium, by the enthalpy change of atomization, we are going to change it from lithium solid to lithium in the gas state, and the fluorine is still as it is. We did not do anything to the fluorine. By enthalpy change of atomization of lithium, we change the lithium solid to the lithium ion in the gas state. And then, by the first ionization energy of lithium, we are going to change the lithium into lithium ion in the gas state, and still the fluorine, we didn't come near it. We are only changing the lithium solid to lithium ion in the gas state. And of course, when lithium became an ion, it released an electron. It released an electron to become lithium ion plus electron. And the fluorine is still as it is. Understand till here, or do you have any question? Do you have any question? Type. Now we come to the fluorine. In order to change the fluorine, half fluorine molecule in the gas state to fluorine atom in the gas state, then this is done by the enthalpy change of atomization of fluorine. And still the lithium ion is still as it is in the gas state, plus electron, plus this fluorine atom in the gas state. Now, after that, the fluorine atom in the gas state will gain this electron by what we call the first electron affinity. So the lithium ion is still the same in the gas state, And now the fluorine gained this electron and became a fluoride ion in the gas state by the first electron affinity. If you see that, we said that the first electron affinity is releasing energy. So that's why you will find that the arrow goes down, because all these arrows were coming upward because all of them were energies required. All these were energies required. But when energy was released, then the arrow came down. Like here, energy is released when lithium fluoride is formed from lithium and fluorine. So the energy is released. So whenever there is energy released, we make the arrow down. When energies are taken in, the arrows are up. Okay? And then what happens? خلاص, we reach the step where we have the lithium ion in the gas state and the fluoride ion in the gas state. So at once, using the lattice energy, the lithium ion in the gas state and the fluoride ion in the gas state will form the solid lithium fluoride. So we call this the Born-Haber cycle. Okay, shall I repeat it? Or you understand it? Type. Okay, of course, they are going to give us all the values. And here, for example, to change lithium solid to lithium gas here, the energy here is equal to plus 161 kilojoules per mole. Here, to change the first ionization energy, it's plus 520 kilojoules per mole. To change the fluorine gas to fluorine atom in the gas state, atomization energy for fluorine, let me write it in red. So it's plus 79 kilojoules per mole. The first electron affinity is minus 328 kilojoules per mole. And of course, they should give us the enthalpy change of formation of lithium fluoride. Maybe they gave it to us somewhere. 1 minute. Yes, the enthalpy change of formation of lithium fluoride is minus 600, and it's minus 617 kilojoules per mole. Now we have all the values except the lattice energy. So we say that the first root, the energy of the first root is equal to the energy of the second root. The first root is the enthalpy change of formation, which is minus 617 equal all the other energies. You know that we take the two roots. We always go tail, head, tail, head, tail, head, as long as the arrows are one after the other, tail, head, tail, head, tail, head. This means that all these arrows are going in one root. The only opposite arrow is the one of the enthalpy change of formation. So here all the arrows are going tail, head, except this. This is head, tail. It's different than those. So all these arrows, all of them are going in the same route. But if you want to continue, two heads are in front of each other. This means that this is a second route. So minus 617 it's equal to plus 161 plus 520 plus 78 minus 328. So plus the enthalpy change of lattice, or the lattice energy. And so if you calculate all these, if you do this calculation, the lattice energy is equal to minus 1049 kilojoules per mole. And as we said, always the lattice energy should be a negative value, because it is two ions bonded together to form a bond. Always bond formation releases energy, and bond breaking requires energy. Do you have any question how to calculate the lattice energy? Type. Okay, would you give me 5 minutes to go to pray and come back, inshallah? Okay, thank you so much.